let's get started so you can all get to lunch early. Thanks for coming, everybody. Thanks for coming to Dublin. First of all, introduce myself. I'm a architect at Hortonworks. By background, I'm a database guy. I started my career at Oracle. I've done various startups and open source projects in data management. I built the Mondrian OLAP engine, which is part of the Pentaho BI suite. I was founder and chief architect of a company called SQL Stream, which was it's still going, but they're doing streaming SQL. I'm also the founder of Apache Calcite, which is a project to build query optimizer technology. It's a framework that you can use to build query optimizer, query planner. It's inside Apache Hive. It's inside Drill. It's in some other projects that I'll mention during the course of this talk. So I'm coming at this, I'm coming at streaming from kind of a bias as someone from a database background. And I often feel, when I'm at conferences like this talking about new technology, I'm kind of the bearer of bad tidings, which is saying, hey, all this cool new stuff, by the time it meets the real world, it's going to look like a lot like the old stuff because it has to, because that's what people understand and that's what works. So streaming is very excited. It is very exciting. But this is a talk explaining why I think the market forces and the technology forces will cause streaming to look as much like a database as it can, without losing what what makes streaming cool. Simply because there are a lot more people out there that can write SQL, that can, for example, write Scala. And I'll describe, what are the technological benefits of that trend. So, yeah, what has SQL got going for it? It's 40 years old. It's a very old language. If you look at the syntax of it, it looks like COBOL, right? And it was designed in the ages of punched cards. It is an old language, but it somehow has this incredible staying power because, well, I think people initially see SQL and they say, well, it's just the way I talk to my database. How big a deal is that? We could design a new API to talk to this new kind of database I've got. It doesn't need to be SQL. What can I possibly lose? Well, kind of below the surface are all of these hidden benefits of SQL and a SQL-based architecture. And in the course of this talk, I'll explain how these benefits pertain to streaming systems the same way as they apply to databases. So kind of the number one is it's a declarative system, so you ask for what you want. When you say a join in SQL, you're kind of asking it to take every employee record and every department record and filter out the ones whose department number on the left happens to match the department number on the right. You don't actually mean it to form that Cartesian product, but what you're saying is, I want you to join these data sets and you figure out the best way of doing it. Use an index if you need to, or whatever. That kind of approach means you need to have a query optimizer because you don't want the system to do literally the query that you wrote. Because it would be incredibly slow. Relational databases were not possible until there were data structures like B-tree indexes and there were query optimizers. But once you have a query optimizer, it gives you all of these things like the ability to reorganize your data without telling your application developers. You can repartition the data or add indexes or so forth. This is very, very powerful. It decouples the different parts of the IT organization and allows you freedom to design an application and build it on 1,000 records and then bring it into production on 1 billion records and tune it as the data sizes change. And then SQL and the relational algebra is mathematically sound. It needs to be that way for the optimizers to work, but because it's mathematically sound, we can write these query optimization rules that are going to preserve the semantics of the query. And lastly, it's standard. everyone knows it. There's a lot of people that know how to write it. So what are the market forces that cause us to use streaming? Even with a stream is more complicated to work with than a database because it's data in motion rather than data at rest. So what are the reasons? If almost anyone given the choice would prefer to work on the data at rest if they can. Why would you use streaming? Well, I think it's the main thing that's driving you is how much your data is worth. Is this data worth more if I act on it within 1 minute than if I act on it within 1 day? If data is hot and has kind of rapidly declining value, then there's a real incentive to work on it as fast as you can, and that means that means producing an actionable response to that data. Declining a purchase because someone is a possible fraud, that kind of thing. As data gets older, it declines in value, which means we tend to move it to cheaper storage. The data that's very, very recent is likely to be updated regularly. It makes sense to put it into memory. As it gets older, we move it to cheaper storage, onto disk, and so forth. And I'm arguing that having a single language, SQL, to deal with both streaming data and data at rest potentially means that we can deal with not just the new data, but combine the new data and the old data. And I argue that the new data and old data combined is worth more than either of them individually. Let's just look at the sources of streaming data. The title of this talk is Internet of Things, and so these devices, sensors and so forth, sensors on our wrists, sensors in our cars, are one important source of streaming data. I actually believe that, and this might be a controversial statement, but I believe the Internet of Things started in earnest about 10 years ago with the introduction of the iPhone. And I actually believe that many of the important I believe the big data revolution was caused by sensor data, i.e. the sensor data coming from people's phones. That's the likes of Google and Facebook were dealing with this data deluge because people were using their phones, all the time, interacting with them. And I think, so in a sense, we already have an Internet of Things data architecture. Hadoop is very well suited for dealing with the huge data volume that come from Internet of Things. The problem of getting the data from low-power devices which are not always connected, that's something that technologies like Apache NiFi solve very well. But once we actually have that data, I think the technology to deal with that exists. And I believe that putting it within a database paradigm as far as makes sense will actually simplify some things. Rather than treating this as a fundamentally different kind of data, let's just say it's the same kind of data, it just hasn't hit disk yet. So in addition to these devices outside of the data center, you've got a lot of sources inside the data center. You've got tracing and logging and so forth. You've got services that are doing operations, producing log files of transactions they're doing, their health metrics and so forth. You've got databases which are maybe not explicitly streaming, but they are writing transactions to their own database log, and we can use change data capture to capture that data. So any process which is writing data is potentially a source of streaming data. And the more of those data sources you can pull together, the more chance you have of being able to solve a given business problem. So here's two very simple queries. The top query is a traditional SQL statement, reading from a table called products. The bottom one is a streaming SQL statement. So the SQL standard doesn't include streaming SQL. I hope that one day it does. But I'm on a mission to get streaming SQL considered as kind of the evolution of the SQL standard. And I'm working with a few Apache projects to do that. The principle here is that it looks, except for that stream keyword, which says I'm interested in changes to the orders, it looks just very much like regular SQL. And that's an explicit goal of streaming SQL, to make it a superset of standard SQL, and to make the standards, to make the standards the same. And another principle is that you can reference regular tables inside streaming SQL. So in this particular case, orders is a stream. And whereas this particular one, if you have 1 million products, it will execute the query, return a result, and then it'll stop. A streaming query runs continuously. It's reading from a stream called orders, and that stream might be populated from Kafka. It might be populated by tailing a log file. It doesn't really matter. It's logically, it is a stream. And it runs continuously, and whenever an order arrives, the system will evaluate whether the predicate is units greater than 1,000. If it is, it'll return it. If it's not, it'll throw it away. The query never terminates, which presents some interesting problems for things like JDBC, where it kind of naturally assumes that things terminate in the end. So stream table duality is an important basis of this. It kind of goes back to some research that was done in Stanford about 10 years ago, proposing some standards for semantics for streaming languages. And their idea was, rather than kind of defining a new semantics for streaming queries, let's define the semantics for streaming queries in terms of relational queries. And kind of one way to describe it is, it's that, for those of you familiar with calculus, it's kind of the time differential of a table. Imagine that you execute this particular query at the bottom. Imagine that you execute this query every millisecond, and you execute it at 10 o'clock and you get 100 rows back. And then you execute it at 10:01 and you get 101 rows back. What will come out of this streaming query is that one row that appears at 10:01 that didn't appear at 10 o'clock. Now, the system isn't literally doing that, but that's the idea, is you can imagine the system's kind of repeatedly executing this query and finding out what's new. And kind of the mathematics of that works out, and you end up with a good semantics for this that allows us to have queries that deal with historical data and future data in the same query. So the stream keyword is the thing that says, I want you to treat this particular use of orders here as a stream, and this one up here as at the top as a table. So the orders table is simply the history of the order stream. And the order stream is simply the deltas, the incoming deltas to the orders table. Does that make sense? Okay. By the way, if you have questions, yeah.
Does that solve the problem of change data capture?
Well, you still need software to actually do the change data capture. But
Can you repeat the question?
I'm sorry. Yes. The question was, does it solve the problem of change data capture? At least it provides a kind of semantics for change data capture. The traditional way of doing change data capture is to write triggers. Triggers are just gnarly code. It's very difficult to look at a set of triggers and say, hey, that works. It's, to verify the triggers are correct. This is a much simpler way of achieving that effect than writing triggers. So I think this is a big advantage over triggers for change data capture. So here's a query that kind of illustrates my point that combining past and future. And someone once said to me, the only useful data are dimensionless values. In other words, ratios of, if a particular stock is trading at 100, is that good or bad? Well, you don't know what its historic. 100 is a good price if it was trading at 25 last week, and not a good price if it was trading at 500 last week. So, and the same applies to, CPU utilization and memory utilization, anything you want to monitor. It helps if you can divide this by, or kind of put this in the context of what the historical value was. In this particular case, we're interested in orders where we're looking at a particular order and saying, is the order is the size of this order larger than the average size of the order of that particular product over the last year? So at the top use of orders, we're using it as a stream. The bottom use of orders, we're using it as a table. We're kind of going back into the history of the stream. Now, the orders at the top is in terms of how the system implements this. Probably the stuff at the top is held in memory, or it's just flowing directly off the network socket. What's below is probably held on disk. Perhaps it's a copy of the stuff in disk cached in memory. It doesn't matter, right? You write this in your application and you leave it to the system to figure out how best to implement this query. Actually implementing it is probably pretty hard because the system has to deal with, what happens when this, the day rolls over and, we need to update these moving averages. So there's a lot of stuff that needs to happen behind the scenes. The nice thing is you as the application writer can write this query and let the system take care of the details. Yep.
If you say that order is on disk, what about the latency? If you say that order is a pre-cached memory table, I understand.
Yeah.
But if it's on disk, what about the latency?
Yeah. The question was, if orders is on disk, what about the latency? There's a particular theme that happens whenever you're dealing with streaming systems is quality of service. So you might the latency is something that you would actually plug into the system and say, what kind of latency am I prepared to accept when running this application? Actually, the parameter you probably add is, am I prepared to accept out-of-date data? Am I prepared to accept something which is 3 minutes out of date? Can I use a cached copy that might be slightly out of date in order to get, a latency of a millisecond as opposed to a latency of a second? If you are prepared to accept that lower quality of service, then you'll get faster results. Streaming systems is always about, there are always compromises to be made. And that's a good thing. It means you're making design decisions. Anyone selling you a computer system that tells you it can achieve the impossible, high latency, high throughput, availability, you can't have all of these, right? But at least expressing it this way, you can then tweak the parameters and say, I'm prepared to accept, delayed results in order to get high throughput, that kind of thing.
That's the important way when you are matching with a trace data, because in streaming the problem is the backlog.
Yeah.
You have to consume backlog, or you haven't backlog. You must have no backlog.
Yeah,
That's the problem.
Why? I mean, that's a design decision too. How important your backlog is to the business requirements.
If you can't consume backlog in a fast way, your backlog is become bigger, and you can't deliver the service in a real-time way.
So that assumes the business requirement is to process that particular backlog for instance.
Yeah.
So you've made a design decision that you have to process.
Well, I think what you're saying is you need to keep up with the throughput. If the throughput is 1 million records per second, you have to have a system that has a throughput of 1 million records per second, because otherwise the backlog will get bigger and bigger and bigger, and you're sunk. So that's why you need to tune these knobs, and you need to make compromises, right? So in order to get the throughput, or you need to buy bigger hardware. So here's a very interesting problem that if anyone is telling you a streaming system, ask them about this. I call it the pie chart problem. Just imagine you've got a stream of data which is arriving. It doesn't particularly matter what this stream is, but in this case, I'm assuming it's orders. And we're interested in how many orders of each particular product have occurred in the last hour. And we want to generate a web page from this, okay? So this is a streaming input. The output isn't a stream. The output is a web page. So when someone hits this web page at 10:05, they want to know how many people bought cheese since 9:05, how many people bought beer since 9:05, and how many people bought wine, okay? Which kind of means the web page doesn't want to look at a stream because the stream only contains one record at a time. They're actually interested in the last hour, which kind of means what you want is a table, an in-memory table perhaps, but some kind of relation, because this kind of goes back to my statement about things being easier on data at rest. If someone is writing a web page makes a round trip, and hopefully it only takes a millisecond to generate this web page. The web page can't sit around waiting for data to come off the stream. It needs to get the data right now. So this is a case where streaming data interfaces with data at rest, that the web page designer actually wants to be looking at a database, because that's the pie chart is an analytic, right? You could, I suppose, write the stream into a table continuously. But probably the best thing is to have it building a kind of a standing table in memory. This is a common application that just about everyone wants to do in a streaming system. Not many streaming systems actually provide a relational view onto the data. I think this is one of the big benefits of streaming SQL. And notice the stream word isn't there. The stream isn't there because I'm asking to query the history, but I'm asking to query a very recent view of the history. You know, the history at 10:05 right now, not the history as it was at 10:04, but I want to see it right now. So this integration of data in flight and making it look like data in rest is one of the advantages of this approach. If you were to use this technology stack for streaming and this technology stack for data at rest, bringing the two different kinds of data together is very difficult. So let's drill into some more of the operations that you can do on streams. And for those of you familiar with SQL, most of the SQL operations make sense virtually unchanged on streams. But I'll explain as I go along kind of what it's kind of some constraints about when you can apply them. So group by is the SQL operation that combines data into totals. So it aggregates data and sums records together. There are various ways of doing group by. The traditional group by, you know, the classic example would be sum together the salary of all the employees in a department. So every employee belongs to one and only one department. They contribute to one and only one total. Multi-group by would be where the employee belongs to perhaps multiple departments through a reporting structure or something like that. And then windowed functions are where an employee, you're interested in the moving average of an order. So, you know, what is the average price of this particular stock over the last 10 trades? So this particular stock here, this trade is going to contribute to the, you know, to the moving average over the next 10. And then this one is going to contribute to, you know, the different set of 10. So each individual record is contributing to a different set of totals. So first of all, let's look at group by. You can't ask a question like, what's the total number of product 100 ever sold? Because the stream hasn't finished, and in fact it won't finish. In streaming group by statements, there always has to be some kind of way of making progress. Often that basically involves including a timestamp in the query. So you're interested in how many orders were there of this product over the last hour or over the last day. Because when that hour finishes, then it's safe for the system to emit the total. Sometimes it's some kind of weaker way of making progress, like since there was the last flush. So maybe the system will say the trading day is complete. Now it's safe to emit the totals. But there's this general idea that totals are over a particular period of time. So we've got this incoming data. As you can see, we've got a record from 9:12 and another record from 9:59. So they both go into this total for the 9 o'clock hour for product ID 100. We've got another record from 9:25 for product ID 130. And then that record that arrives at 10 o'clock is going to go into a 10 o'clock total. The 11 o'clock hour has not arrived yet, so that 11 o'clock record is basically waiting until the 11 o'clock hour is complete. So when a row is emitted, there's this idea that I call it the replay principle. And it's kind of the kind of basis for streaming SQL being sound semantics. Is if you were to take the same query, if you record the history of a stream and write it to a database table, and then run that same query on the database table, you should get the same results. That's often difficult to achieve for people that are implementing these systems because data sometimes arrives out of order, and sometimes you even get data records arriving twice. But it's very important principle for the application developer that you're getting sound semantics. You get if you run the same query twice, you'll get the same results. And if you run the data if you want to test your application running on historical data sets, you get the same results. So the streaming query should produce the same results as running in the non-streaming query on the same table. And that also implies you're not relying on implicit information, such as a flush signal arriving in the stream, or behaving in a particular way because of the relative arrival. If you're joining two streams together, if this record arrives before this record, you emit it. But if this one arrives before this one, you don't emit it. Any of that kind of stuff is not useful for the application because the application is going to behave in a different way depending on just random stuff that's happening on the network. And as I mentioned, we allow a streaming query if we're able to make progress. We don't want to accept something which says, tell me all orders of this product, because we don't have them yet. We don't have to have the full history available, but we have to know when kind of a little piece of history is finished, and then we can emit a record and make progress. Monotonic columns, if we know, monotonic is a fancy word for ascending or descending. So if we know that the row time column is strictly ascending, then if we've just seen 1101, then we safely know that 1059 is not ever going to occur in the future, and therefore we can safely emit the 9 o'clock to 10 o'clock hour. Sometimes you've got columns which are almost monotonic. In other words, you know that the row time column is within 5 minutes of being ascending. So if you've just seen 1106, you know you're not going to see a record that's before 11 o'clock. If you've seen 1101, it's still possible that a 1058 record could arrive. And there are other things like punctuations and watermarks that various systems support. I talked to the folks from Apache Flink. They're big fans of watermarks, which are a form of punctuation, a kind of declarative way of sending data through the system. Streaming SQL is kind of big enough to accommodate those forms of things. But basically, if you as a user try and execute a streaming query like this, it actually says requires at least one monotonic expression. But the basic idea is it needs to know that it's able to make progress. Otherwise, it will refuse to run the query. If it did run it, you'd just be looking at a blank screen because it would never be able to produce any results. So you would be unhappy eventually. Window types. So I discussed group by queries, but windowed aggregation is this idea of being able to sum up the previous 10 records of the same product, that kind of thing. Moving sums and moving averages are very important and popular. The different window types allow you to define which set of records go into the window. So a tumbling window is probably the most common. So every minute, emit a total for that minute. A hopping window is kind of a generalization of that. For example, every minute, emit the total for the last 10 minutes. So at 10 o'clock, we'll emit the total for 9:50 to 10 o'clock. At 10:01, we'll emit the total for 9:51 to 10:01, and so forth. And so forth. I know the Flink folks are doing a lot of work on allowing people to define their own window types, we're putting that stuff into streaming SQL. It remains to be seen kind of how broad a definition of window types people actually end up using in practice. I have a feeling that with things like tumbling and hopping and sliding windows, it probably covers 98% of the use cases, but we'll see. And then window functions. This, if we remove the word stream from there, that is standard SQL. It's a bit verbose, but hey, that's standard SQL. The basic idea here is the partition by product ID is saying I'm not interested in the sum of and here we've defined a window here which is saying over the last hour. And then the partition by product ID, we're saying over the last hour, and furthermore, only consider records within the same product ID. So at 10 o'clock, we're going to, if we receive an order for product 100, we will emit the sum total of orders for product 100 over the last hour. And if we receive an order for 200, then the total emitted will be for orders of product 200. It kind of makes sense. The way of expressing it in SQL syntax is a little complex, but hey, that's standard SQL. Various kinds of joins are possible. Joining a stream to a table is kind of what you'd think of as a lookup. So in this particular case, we've got orders, which is a stream, and products, which basically contains a price list. You think of it as a lookup. You could imagine caching the products table in memory, and every time an order arrives, we do a lookup on product ID to find the kind of list price of that product. It gets interesting if products is larger than memory, and then that's a nice challenge for the person writing the streaming system, how to deal with that. Again, expressing this in streaming SQL allows you to offload that challenge onto the database engineer writing this, and the application engineer doesn't have to worry. Yeah, and then joining a stream to a changing table. This gets really interesting. So let's suppose that you have while these orders are being received, someone is updating the price list. And what happens if you take an order at 9:45 and the product is $10, and then at 10 o'clock the system crashes, and then at 10:15 we want to replay the query, and the price list table has been updated. So when we replay the query, this product is now $12. In order to have that, fulfill that contract that replaying the query produces the same results, we probably need temporal database semantics, some way of the system looking at the table as it was at 9:45 when it replays that query. This is a hard problem. I'm not offering a solution here, but I'm saying, just using this 6 lines of SQL, we can express that problem, and then we can push that down to the streaming system and say, I want transactional semantics. Or I don't want transactional semantics because I want my query to run fast, and I'm prepared to accept, the system lying to me in these circumstances. And then joining a stream to a stream, which is a kind of a different case entirely. So the example I use here is, well, when we join a stream to a table, you can join the stream to the entire contents of the table because the table is there. You can't join an entire stream to an entire stream. So inevitably, when you do a stream-to-stream join, there's always a time component. In this case, the time component is we're interested in shipments that occur within an hour of the order being placed. So if the order is placed at 10:15, then the shipment has to occur between 10:15 and 11:15. That's useful for the system because it means that at 11:15 it can drop that order from its hash table. It's also useful for the business because if we had to wait forever to see whether that order was shipped, most businesses actually have these kind of rules built into the business. Accounting practices, all these people who hassle you because you don't turn your expenses in on time, it's because they have accounting rules that they have to move these liabilities off the books within a certain amount of time. Businesses have rules for timely delivery of things. So often, it might seem like a hardship to put these time constraints into the query, but often the business owner that's telling you to write this query will actually know what those time values are because they've already figured them out as part of the business process. So query planning. This is kind of goes to my what I do day to day. Helping build the Hive cost-based optimizer, Apache Calcite, and so forth. I thought I'd give you just a kind of a quick look into what happens. So, and the nice thing is it's kind of surprisingly similar between streaming queries and regular queries. So we decompose the query into relational algebra. Joins, filters, aggregates, table scans, and so forth. This is actually not a streaming query, but it's an illustration of a hybrid query, querying data in Splunk and data read from MySQL via JDBC. And so this SQL statement here becomes these relational operators. And if you'll notice that we are applying a filter, action equals purchase, after the join. Now this action column exists in, I think it's the Splunk table. So we can push the filter through the join and actually and have it execute inside Splunk. So actually what's happened there is we've fired two transformation rules. Calcite is kind of full of these transformation rules that can transform relational algebra into something which preserves semantics but is more efficient. And if you have 200 transformation rules and some cost functions, then that's what a query optimizer looks like. And Calcite is an engine that allows you to do this kind of query optimization. Many of these optimizations that you can apply to tables, you can also do safely to streaming queries. I'm going to skip over this, except to say Calcite is kind of like a regular database, but stripped down to the query optimizer. So the data sources and the metadata is all stored externally. So that allows you to embed Calcite in something like Hive or Drill. And we're using hcatalog to get the metadata, and we're using Hive's operators. And Calcite is just able to optimize the queries given the rules and the data sources that Hive is providing. So summarizing relational algebra, all of the core operators on the left-hand side of relational algebra apply to streaming, and then we've got extra ones. These are kind of theoretical operators, but we've got an operator which converts a relation to a stream and another operator which converts a stream back to a relation. The stream keyword in the SQL kind of represents this delta operator. And that set of operators is enough to optimize, to represent and optimize any streaming query. Don't have much time left, but I guess it might surprise you that even something like order by can work on a stream, as long as the system is able to make progress, which means you can say order by stuff within the last hour. You just can't say order everything over all time. Things like union and union all and so forth also work in streaming SQL. So in summary, streaming SQL kind of extends standard SQL to deal with relations and streams together, not just relations. And queries are valid if they have some time-based component or some other function which is pushing the data through the stream and allowing the system to make progress. And the benefits of streaming SQL, it provides a high-level language to deal with IoT applications. It allows you to kind of tweak the knobs by saying what quality of service you want. And it allows you to combine real-time and historical data. So this is a work in progress. We are building it into various projects, Flink, Storm, Samza. Actually, the Flink is a work in progress. Storm already has a SQL interface based on this, and Samza also has a SQL interface based on this. I'm trying to form a broad coalition of people that are building streaming systems. The idea is that we end up with a lingua franca that kind of allows all of these various streaming systems to present their unique capabilities, but within something close to a standard language. That's all I have. There's probably a couple of minutes for questions. Please come to my talk tomorrow, Planning with Polyalgebra. I'm talking about extending relational algebra to deal with not just streaming, but complex data such as documents, machine learning, and schemaless data. So thank you very much.